By 1943, Japanese fighter designs, once dominant, faced increasingly lethal competition in the Pacific theater. Early design priorities that emphasized lightweight structures and extreme agility had become critical liabilities against heavily armed and durable Allied aircraft. A close examination of combat data and captured Allied technology forced Japanese engineers to implement key technical shifts, moving away from maneuverability-focused philosophies toward heavier, more survivable, and powerful platforms. A primary vulnerability in early Japanese fighters was their near-total lack of protection. This deficiency was addressed in two key areas: self-sealing fuel tanks. Early models of the Mitsubishi A6M0, including the A6M2 and A6M3, lacked self-sealing fuel tanks entirely. Their wing and fuselage tanks would frequently ignite after sustaining only a few hits from .50 caliber machine guns. Influenced directly by examining damaged yet intact Grumman F4F Wildcat and Curtiss P-40B Warhawk aircraft, Mitsubishi introduced laminated, rubber-coated tanks starting with the A6M50. Although less effective than their American equivalents, this marked the first significant fire protection system in the Zero lineage. Pilot protection. The original Zero's design philosophy sacrificed pilot protection for maneuverability, a trade-off that resulted in a disturbingly low pilot survival rate by late 1943. In response, the A6M5C variant included a 45mm steel backplate and armored glass for the canopy, though these were still thinner than US standards. Newer aircraft, like the Mitsubishi J2M Raiden Thunderbolt, incorporated more robust seat armor and rear fuselage plating. These features mirrored those of Allied fighters like the Grumman F6F Hellcat, which often returned to base with cockpit damage that would have been fatal in earlier Japanese models. Initial Zero models were known to suffer catastrophic structural failure in dives exceeding 400 knots. The dive and zoom tactics employed by P-40 and F6F pilots fatally exposed this limitation. To counter this, the A6M5 variant received reinforced wing spars and a thicker 1.5mm wing skin, which raised its redline speed to a more competitive 460 knots. Similarly, the Kawanishi N1K2 Shiden Violet Lightning adopted a simplified, high-strength airframe with improved load tolerance. When facing formidable heavy bombers like the Boeing B-17 Flying Fortress and consolidated B-24 Liberator, the light machine guns of early Japanese fighters proved insufficient. This led to significant armament upgrades. The A6M5C added two 13.2mm Type 3 heavy machine guns to supplement its standard two Type 99 20mm cannons. The J2M Raiden and N1K2 Shiden were equipped with a powerful battery of four Type 99 Model 220mm cannons, featuring improved ammunition feed systems. This increase in firepower was a direct response to the heavy armament seen on Allied fighters, such as the 6.50 caliber machine guns found on Hellcats and P-51 Mustangs, and was intended to increase success rates during interceptions against Allied bombers. The Mitsubishi Kasei engine in the J2M Raiden initially suffered from severe thermal regulation issues at low altitudes. Lessons learned from the sophisticated turbo-supercharged intercooler systems of the captured P-40B's Allison V1710 engine prompted modifications. The Raiden's cowling was redesigned with new intake geometry, cooling gills, and enlarged oil coolers. While not as efficient as the American systems, these airflow improvements helped reduce engine seizures, particularly in tropical climates. Early Japanese cockpits featured high rear decking and heavily framed canopies, which severely restricted pilot visibility. In contrast, American fighters like the North American P-51B Mustang and Republic P-47D Thunderbolt introduced low-profile bubble canopies with minimal framing. Observing the tactical advantage this provided to U.S. escort pilots over the Philippines and Marianas, Japanese designers adopted cut-down fuselages and clear-view bubble canopies for the Nakajima Ki-84 Hayate Gale and the Kawanishi N1K2 Shiden. This change drastically improved situational awareness in high-speed dogfights. The Nakajima J1N1S Gecko Moonlight Night Fighter was fitted with the Type 3 Ku-6 air-to-air radar, identifiable by the dipole antennas on its nose and wings. This rudimentary system was Japan's response to the SCR-520 radar, seen on American P-70 Havoc night fighters and modified TBF Avenger patrol craft. Although its range, typically under 3 kilometers, and reliability were limited, it provided a nascent capability for night interceptions against Boeing B-29 Superfortress bombers. The radar program expanded in 1944 to 45, though it was ultimately too late to counter U.S. nighttime bombing campaigns effectively. Ultimately, the evolution of late-war Japanese fighters reflects a fundamental shift in design philosophy. The initial focus on tight turn radius and climb rate gave way to a prioritization of roll rate, structural integrity, and energy retention. The J2M Raiden, with its short, reinforced frame and high wing loading, sacrificed turn performance for exceptional high-speed climb and diving capabilities. The N1K2 Shiden was a simplification of its predecessor, designed for easier maintenance and improved durability. Both designs emerged as direct answers to encounters with robust American aircraft that could outlast and outgun earlier, more agile Japanese models. From fuel protection to airframe reinforcement, nearly every major improvement in Imperial Japan's late-war fighters can be traced to direct encounters with U.S. aircraft. The combination of captured wrecks, combat analysis, and changing battlefield needs pushed Japanese aviation from light, maneuverable airframes toward heavier, more powerful, and survivable platforms. A story of rapid adaptation driven by necessity.